a quick recap of what we were doing in the last class. So we did a few examples where we applied the principle that we've been discussing so far, namely that if we are interested only in the output samples taken at n times ts, when you drive an LPTV network uh, with a, an input. So, we saw that this is equivalent to taking that input Vi of t and exciting an equivalent LTI system with Vi of t and sampling the output of that at n times Ts, right. And how to find H equivalent of t? We basically said, okay, we form the adjoint network n hat LPTV at Fs and we excite the output port with delta t and the voltage that is developed is H equivalent of t. All right. So, today we saw the example of how one can use this to advantage in a switched RC network as well as a first order continuous time delta sigma converter. If you haven't seen a continuous time delta sigma converter before, then you just think of that system as a simply an LPTV system, and we saw H equivalent of t. Today, we will look at a different situation where for instance, again concerning sampled LPTV networks, and I would say it is simply an extension of what we have seen already. So, we have a network, again we have an input current and an output voltage. And we are, let us say we are not interested in V out of NTS, but we are interested in, so the output of interest is V out of NTS plus some T naught, where T naught is greater than or equal to 0, less than or equal to less than Ts, right. So, in other words, the frequency of sampling is the same as that at which the network is varying, right, except that earlier we were interested in sampling at multiple, I mean at 0 Ts and so on. Now, you know, a reasonable question to ask is what happens when you sample with an offset. So, this is called offset sampling, and T naught is the timing offset. All right, and as usual, we have seen, I mean, so remember that the LTI system or LPTV system is H sub k of j 2 pi f e to the j 2 pi k f s times t h sub minus k j 2 pi f e to the minus j 2 pi k f s into t . So, this is let us call this some I n of t, this is V out. Okay. But we are only interested in V out of n t s plus t naught. So, we are so in other words we are sampling this output, this is V out of t and is being sampled at n t s plus t naught. Okay. So, as usual, as we have done before, we will simply move the sampler inside, and so the moment you sample this, you basically you will now get j 2 pi k f s times t naught, right, and so likewise you here also you will get this times t naught, right. And the reason is that when you evaluate this factor at n t s plus t naught, that n t s becomes a integral multiple of 2 pi, and this is just what is remaining is just t naught, correct. So, now does this depend on time, or is this independent of time?
That is a complex number.
It is a complex number, but this is independent of time, right. So, does not vary with time, right, and is therefore it is simply a fixed number, and therefore you can think of this therefore as taking I n of t, passing it through a h equivalent of h equivalent hat of j 2 pi f, right. I use the hat because it is different from what we obtained when t naught was 0, right, and the output of this is sampled at n t s plus t naught. So, you get V out of n t s plus t naught, all right. And what is h equivalent hat
Summation
of j 2 pi f is simply the sum over all k of h sub k of j 2 pi f e to the power j 2 pi
KFS.
k f s times t naught, all right. Sanity check, if t naught is 0, you should simply get sum of the harmonic transfer functions, all right. Now, the question is, okay, so as usual the question is how do we find h equivalent hat of j 2 pi f, or equivalently the time domain h equivalent hat of t, all right. So, our situation is like this. So, we have an LPTV system, right, let us say V I of t, and this is the network, right, and we have V O of t. Let me just use, since we are talking about currents and voltages, let us do that. So, this is 1, 1 prime, 2, 2 prime, V out of t, all right. And this is sampled at so we are interested in finding the samples, and we know that this is exactly equivalent to finding equivalent to an LTI filter whose impulse response we want to find. So, so if you excite, if I in of t is so the impulse response of the equivalent, so let us say I in of t is the input, you have some LTI system H equivalent hat of t, and the output is sampled at NTS plus T naught. Okay. So, this is V out of NTS plus T naught. Okay. So, if I want to find, so if I apply an input delta t, right, the output waveform here will be H equivalent hat of t. So, the sample here will be, the first sample here will be H equivalent hat of T naught, correct. But if I want H equivalent hat of 0, what should I put in? At what time must I excite the system?
That is t plus t naught.
You can't have t plus t naught in the
Like before we have done.
no. At what time should I apply the impulse, correct, so that I get H, when I sample the output at t naught, I get H equivalent of 0.
T minus t naught. Delta of t minus t naught.
That is, so
And
if I apply delta of t minus t naught, in other words, I must apply the impulse at
after t naught. We have
at
to
t naught, correct. So, if I apply the impulse at t naught, then what will I get here? I will get H equivalent hat of
t minus t naught.
t minus t naught. So, if I sample it at t naught, I will get H equivalent hat of 0. Do you understand this? So, all right. So, in other words, so impulse applied, right, and sample value at t naught. Let me just do that. Correct. So, if I apply the impulse at t naught, the sampled value of the output at t naught will be
H equivalent of 0 and H equivalent at of 0.
0. Okay. Now, if I want if I want the sample to be H equivalent hat of delta t, where delta t is some small number, small time, at what time should I apply the input?
There-
Do you understand the question?
Yeah, I understood, sir. Like we have to apply that t naught plus t naught minus delta t. We have to
Very good. You have to apply it at t naught minus
delta t.
delta t, correct. If you want to see H equivalent hat 2 delta t, you must apply
T naught minus 2 delta t.
t naught minus 2 delta t and so on,
Like here,
right. So, therefore, so again we see that we are changing the inputs, but our output measurement is always the same. So, that basically means that you can exploit the adjoint again as expected, right. We did the same thing with the case when t naught was 0. Now, we will do this, it is the same, sorry. So, this is basically n and this is n hat, this is the adjoint. This is also LPTV at Fs, and this is the adjoint network, right, and this is 2 and this is 2 prime, and what should I do? Now, in the once you, we already know how to find the adjoint, you do time reversal of all the control signals and so on. And so, remember if you apply an input
0.
at T1, so original, or rather let me call this, for a network N, if you apply the impulse at T1, measure at T2, right, it is the same as, you will get the same result if in the adjoint
Apply
impulse at minus T2, measure at,
minus T.
right, and you must apply the impulse at the output port of that joint, right. So, what should we do now at so, in this experiment, this is corresponding to N, we are going on changing the instants at which the
Input
input
is
is applied, but the measurement remains the same. So, in that joint, the
input has to be
input has always to be applied at what time?
T naught minus T naught.
Minus T naught. So, we will apply therefore a current of delta of T plus T naught, right, and if you measure the output of the adjoint at T naught, what will you get at I mean sorry, to get, when will you see H hat equivalent of 0 in the adjoint?
Minus T naught.
At minus T naught, right. So, what is the waveform that you will get there at the output?
There H equivalent of
H hat equivalent of
T plus T naught.
T plus T, right. So, in other words, in the adjoint, what you do is, if I want to draw a picture, what you would like to do is you apply an input or at minus T naught, right, and what will happen? Well, the output waveform will do something like this. So, what is the to get H equivalent hat of, this is H equivalent hat of T plus T naught. That basically means that H equivalent hat of T has been moved to the left by T naught. So, H equivalent hat of T therefore is, you take this so this is going to be, you shift it to the right, this is H equivalent hat of T. Correct. So, this is how you determine the equivalent impulse response of the system, or rather the impulse response of the equivalent LTI filter, if the
Sampling is offset.
the sampling is offset. That makes sense.